Okay, great. All right. Can start then. Yeah, so today we're going to talk about the 4 problems from BMT. I was thinking about starting with the one that involves an 8-unit simplex. Let me just quickly open it. So I assume everybody who wanted to join joined already. So we're starting. If you guys have any questions, feel free to unmute yourself or type in the chat. Yeah, so the problem with 8-unit simplex in a 7-dimensional space is that if you consider generally an n-unit simplex in R n-1, then it does not generally have nice coordinates. And by nice, I mean, well, rational, because if we look at an equilateral triangle in R2, then it would have coordinates like 0, 1, 1/2, √3/2, and -1/2, √3/2. And there's really no way around it to avoid an irrationality. So which makes it really difficult to work with n-unit simplex in R(n-1). So if you imagine a tetrahedron in R3, it will not have like a nice coordinates as well. So the trick here is instead of considering an n-unit simplex in Rn-1, we consider n-unit simplex in Rn. So for instance, if we look at equilateral triangle in 3-dimensional space, we can position it in that way that it will have all coordinates so if we position an equilateral triangle like on the picture, then the coordinates of it will be just so this one, this one will have coordinates this form, and this one will have coordinates of this one. All right. So this is something that it is much simpler to work with. So we will just consider a general n-unit simplex in sorry, can you guys see my screen?
I can't see it. I think you stopped screen sharing.
Yeah. Yeah, so let's consider n-unit simplex, general n-unit simplex. And we're basically, the problem asks us to find a radius of a sphere such that the n-unit simplex is inscribed in it. Okay, so yeah, let's consider endpoints in Rn that have coordinates as following. Like this. So these will be equidistant. In fact, distance between any two of them will be root 2. So I hope it is clear why they're equidistant. If not, you can guys ask questions. Yes, so this will be an n-unit simplex scaled up by a factor of root 2. So I'm just considering these vectors because it is much easier to work with something that has coordinates 1s and 0s. Yes, and so we will find a radius of a sphere such that these points are inscribed into it. And then we will divide it by root 2 because this is a scaled up version. So the center of this figure, it will be point M equal, so just the sum of all coordinates divided by n, which is equal to, has these coordinates. So this will be the center of the sphere, of the hypersphere that we're looking for. So the distance between each point, yeah, let's label these A1, A2, A3, AN. So the distance between each point AI and M will be the same. So for instance, the vector A1M looks like minus n divided by n plus 1 and just bunch of 1 divided by n. So the length of it will be square root of and n times this. So we have basically sorry, why? So it should be this. And here, this should be n minus 1 squared divided by n squared. So we have one term like this, and then we have n minus 1 terms of this form. Okay, so we just rearrange some terms. And what we get is, in the numerator, we will get n divided by n times n minus 1. And in the denominator, we will get n squared. Okay, and then so the value of it is just this. So, and remember, we have to scale down by root 2 because we considered an n-unit simplex scaled up by root 2 in the beginning. So our radius that we're looking for is just n minus 1 divided by 2n. So in our problem, n is equal to 8, I think. So the radius will be just root 7 divided by 4. Yeah, and we have just a general formula for n-dimensional space. All right, so if you guys have any questions, feel free to ask. Yeah, let's talk about the problem involving generating functions. So this is a pretty typical scenario where generating functions come up with in the combinatorial scenario. So we have this was the first problem. Now this is the second problem. So we have AD defined as the number of solutions to A plus B equals D, and A has to be congruent to B mod N. All right. So then we're asked to then we define polynomial like this. We are asked to evaluate this polynomial at 0. Yes, so first let's consider so parity of n matters. So AD would depend on the parity of n. So we will consider n even because this is an easier case, and we will see why it is sufficient to just consider a case of even n, and we don't have to consider n odd at all. We'll see that later. So suppose n is even, all right? So then A plus B equals D, and A is congruent to B mod n. So from these two, an obvious consequence is that 2A is congruent to D mod n. So if D is odd, then this equation has no solutions. So if D is odd, then AD is equal to 0. Why? Because we have some even number has to be congruent mod n, which is even, to some odd number, which is impossible. So just AD is equal to 0 whether D is odd. So if D is even, then we have one obvious solution to this system, which is A equals B equals D over 2. All right. So in this case, A and B are congruent mod n, obviously, and also their sum is equal to D. Yes, so my claim is that if A prime, B prime is a solution, another solution, then it has the form of n kn plus D over 2 minus kn plus D over 2. So why is that? Well, it's not that complicated because so we know that A plus B is equal to D and A is congruent to B mod n. Then we have 2A is congruent to 2B is congruent to D mod n. All right. It means that well, 2A is even, n is even, and D is even. Then this is the same as saying A is congruent to D over 2 mod n over 2. A is congruent, and it is congruent to B mod n over 2. All right, so A is then d over 2 plus k n over 2. And b is d over 2 has to be minus k n over 2 because they have to sum up to d over 2. Okay, so then yeah, let's check that for these a and b, the second condition hold. So a mod n is equal to d over 2 plus k n over 2. It is congruent to d over 2 minus k n over 2. So these are congruent because n over 2 mod n is congruent to minus n over 2. So these always satisfy our system of equations. Oh yeah, sorry. So this was supposed to be k n over 2. And yeah, this was supposed to be minus k n over 2. Yeah, okay. Then we just have to watch that both of them are non-negative integer. If I remember correctly, yeah. So we are interested in non-negative integer solutions. So yeah, so this means that d over 2 plus k n over 2 has to be greater or equal to 0, and d over 2 minus k n over 2 is greater or equal to 0. So this is equivalent to k being in the interval minus n divided by, no, minus, so floor function of d over n to floor function of d over n. So this is an interval to which k belongs. So I hope it is clear why. If not, you guys can ask questions. Yes, so we're interested just in the number of solutions. So we have to count integer points in this interval. So from this, AD is equal to 1 plus 2 d over n. So because this interval contains floor function d over n negative points, 0, and also floor function d over n integer points. So now we have figured out AD, which means that we know what m of t is equal to, our generating function that we're interested in. So our generating function m of t is equal to the sum for d even of 1 plus 2 d over n x to the power of d. All right. Yeah, so now we wanna convert this infinite sum into something that we can work with, basically. So we wanna fold this generating function into a regular expression. So here's how it's done. So we just investigate the structure of this generating function. So note that this value changes. So this value is the same when d is from 0 to n. It is the same when d is greater than n, less than 2n. It is the same when d is greater than 2n, less than 3n, and so on. So our generating function looks as following. So for d from 0 to n, this value is just equal to 0. So this is just 0. d over m floor function is equal to 0, and this expression is equal to 1. So we get 1 times x to the power of 0. And also note that we're only interested in even powers because the coefficients of odd powers are 0. We proved that previously. So this continues until we reach n minus 2. So when d is, okay, so this corresponds to 0 less or equal to d less than n. So now this will be the case n less or equal to d less than 2n. So the coefficient becomes 3. So this is 3 x to the power n plus x to the power n plus 2, and so on to n minus 2. So similarly, we will have 5 x to the power 2n, 2n plus 2, all the way to x 3n minus 2. So you probably already see a pattern. So this will be our generating function. So each of these we can collapse into a single expression using the because it is a geometric progression. So we just use the formula for geometric progression to collapse it into something. So we get x to the power of n minus 1 x squared over 2 plus 3 times x to the power of n minus 1 over x squared minus 1 plus 5x these are from BMT, which stands for Berkeley Mathematical Tournament. Spring, this one I think is spring 2016. Yeah, so yeah, this was x to the power 2n and multiplied by the same expression. So we're just collapsing these sums into a single expression using the geometrical formula for geometrical progression. Okay, so we note that we can factor out this term as it appears everywhere. So this can be factored out, and then we have 1 plus 3x to the power of n plus 5x to the power of 2n, so on. So okay, here we will stop our equation chain and we will just observe this more closely. So let's consider a function. Yeah, I wrote t for some reason, but then I wrote everything in x, so I'll just change that to x. So let's consider a function fx equal to 1 plus 3x plus 5x squared plus 7x cubed, and so on. So this is just f of x to the power of n. So first we will figure out what this equals to, and then we will plug in x to the power of n instead of x, and this will be the value that we're looking for. So first of all, we can break it into two parts. So you can separate this well-known generating function. And this would be plus 0 plus 2x plus 4x squared plus 6x cubed and so on. So first part of this expression. So I don't know how well you guys are familiar with generating function, but the first part is just, it is well known that is it is 1 over 1 minus x. So second one, first thing we do is we factor out 2x. And what is left is 1 plus 2x plus 3x squared plus 4x cubed plus and so on. So yeah, we have to figure out what this guy is equal to. So the general term of this generating function is nx to the power of n minus 1. You may have seen this when we perform differentiation. And so it turns out that you can differentiate generating functions like you just generate sum of functions. So this is a trick that is often used to figure out what the value of generating function at some point is. So this is just d over dx of the sum of xn, where n goes from 0 to infinity. So yeah, if we generate each term separately, we just get this. So that's why the generating function above will be the derivative of the generating function below. So we know what this equals to. It is just so d over dx of the value of this sum is just 1 over 1 minus x. Okay, so if we generate it, if we differentiate it over x, then what we get is plus 2x times 1 over 1 minus x squared. All right, so the value of our fx is just 1 plus x over y minus x squared. So remember, this was just our function fx. We're interested in the value of f of x at this one. So we'll just continue. Over here. So we had x to the power n minus 1 over x squared minus 1, f of xn. So which is equal to x to the power of n minus 1, x squared minus 1 times 1 plus x to the power of n over 1 minus x squared. 1 minus x to the power of n squared. So these two cancel, and we get something like this. X squared minus 1 times 1 minus xn x to the power of n minus 1. Okay, so now we have to find the value Pn. So Pn, we're told, is just the limit when x approaches 1 of n times mx minus 1 over 1 minus x squared. So now when we figured out the value of mx, now this becomes just a regular limit that we have to evaluate. So we get limit when x approaches 1 of n 1 plus x to the power of n divided by x squared minus 1 x to the power of n minus 1 minus 1 over 1 minus x squared. All right, so this is equal to x approaches 1. So we have x minus 1 squared here, and we do have x minus 1 squared here in the denominator, because this part is divisible by x minus 1, and this part is divisible by x minus 1. So let's factor out x minus 1 from both of them. So what we will get is, if we factor out, get this, we'll get x plus 1 here, and we will get the sum 1 plus x squared plus x to the power of n minus 1 here, minus 1. All right. Wait, this was actually, I think this was actually a bad idea, because now we have this big sum. So let's factor out just one x minus 1, and we'll leave the second one. It doesn't change the result, just these are more neat to, like, these are more comfortable to work with. That's the only difference. So yeah, we have this limit. Let me shorten it a bit. Minus 1 over x. Okay. So one over x. Here we get x plus 1 times x to the power of n minus 1 times, sorry, this is supposed to be x minus 1 here, x minus 1 here. Yes. X minus 1. So in the numerator, we will have this. And this, we subtract x plus 1, x to the power of n minus 1 from it. Right? Yeah, and we multiply this by x minus 1 as well. So x minus 1 and 1 plus x to the power of n. Okay. So we just have to evaluate this limit now. X plus 1 x minus, yeah, this is supposed to be x minus 1. X minus 1 squared, x to the power of n minus 1. Yes, I think we'll have to divide the numerator by x minus 1 regardless. So yeah, let's just divide numerator of this and denominator of this by x minus 1. So what we'll get is the second power disappears, and we will get n1 plus xn minus x plus 1 times this sum. All right. Yes. Okay. So now we note that x equals 1 is a root of numerator. So this shows us that we're basically on the right track with things. So yeah, because if we factor out x minus 1, then the numerator will the x minus 1 in numerator will cancel with x minus 1 in denominator. Right? Actually, we can just apply, I'm thinking about applying L'Hopital rule here. Yeah, I think that will work. Yeah, we can just apply a L'Hopital rule twice, right? It's going to be kind of messy, but I think this is better than just factoring out x minus 1. Yes, okay, so yeah, to apply a L'Hopital rule, we can yeah, so let's express this as x to the power of n minus 1 divided by x minus 1, and denominator will be this. Okay, and to make it easier for us, for ourselves, we can also do the following thing. So we can this factorizes as x minus 1 times this big sum. Okay, so we can just factor out this and evaluate them at x equals 1, and this will not change the value of the limit. All right, so we can just, this is like a limit of product is product of limits. So because the limit of this guy and this guy exist, then we can just factor them out. So we'll get 1 over 2n, and expression in the numerator will look like this. X minus 1 divided by x minus 1 squared, basically. So yeah, now we apply L'Hopital rule. So n times 1 plus x to the power of n plus x plus 1 x to the power of n minus 1 over x minus 1 prime is equal to n squared x to the power of n minus 1 plus, so this will be one of terms, and So we're just differentiating the product. So this guy will be equal to x minus 1 squared. So n times xn minus 1 times x minus 1 minus x to the power of n minus 1. Something like this. All right. Yes, so let's evaluate this. Plus n x n minus 1 x squared minus 1 minus xn minus 1 times x plus 1 over x minus 1 squared. All right, so this is what numerator will look like after we differentiate it once. So I'm just trying to think of any way we can simplify it, but I don't think there is a way. Yeah, so now we have to apply the L'Hopital rule the second time. So we have to differentiate this second time, and then we will be almost done. So when we differentiate it the second time, we get n squared times n minus 1 plus so x to the power of n minus 1 over x minus 1. We already took derivative of that, which is this x minus 1 and over x minus 1 squared plus, so we have to now differentiate this guy. Okay, so we will have x minus 1 to the power of 4 in the denominator, and in the numerator we will have so derivative of numerator we first have to take. This will be n times n minus 1 times x to the power of n minus 2 x squared minus 1 plus 2n x to the power of n minus 1 no, just x to the power of n minus nx to the power of n minus 1 times x plus 1 minus x to the power of n minus 1. All right, so this we have to multiply by x minus 1 squared. The second term will be minus 2 times x minus 1 and just multiply by the numerator. And x to the power n minus 1 x squared minus 1 minus x to the power of n minus 1 times x plus 1. Okay, now we would have to evaluate all that. I'm just thinking, is there another way of doing it? Another way of evaluating this guy. So just what's left in the solution is that we have to evaluate this limit the fastest way possible. Then we're gonna get some kind of polynomial of p of n. So we claim that this is our polynomial that we're looking for because we know its value for any even number. So we know its value in infinitely many points. So we know its value in any other point. So we just plug in n equals 0 and we're done. All right. I'm thinking we can cheat because, okay, if Pn is this, we're just interested in finding P of 0. So we can just plug in n equals 0 into this. No, never mind. So we have to evaluate this. If you guys have any ideas how to do it easier, then you can just write in the chat. Okay, so this second fraction, we will have something of the form, this form. So we will have n x to the power of n plus n minus x to the power of n minus 2 plus 2x to the power of n minus 1 plus 2x plus 1. So this is just, we look at this expression, and when we can divide it by this guy. So again, we can just evaluate this guy at point x equals 1, which will simplify our expression. So this is just 1 over 2n and the limit of this guy. plus n minus this expression. Yeah, so we have just x minus 1 squared into the denominator. So what we can do, one thing we can do is we can pair xn with every power that we have in the right, xn minus x, okay? And we can pair, we can divide n into n ones, and we can pair them as well. This would give us the following expression. Okay, so we have to divide it by x minus 1 squared. So okay, the limit will be equal to this. So in every expression involving xn, we can factor out some power of x. So in this case, we can factor out x to the power of n 1 minus 1. In this case, we can factor out x, and so on. In case of x to the power of n minus x, we can factor out x minus 1. So then these guys, we can flip their signs, and we will get something like this, minus n minus 2 minus 1 minus dot 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 1 minus 1. I'm specifically keeping 1 minus 1 for a reason. So and divided by x minus 1 squared. So 1 over 2n, we group terms from the first part involving to the terms in the second part involving the same expression. So for example, we group these together. So, and what we will get is, we will get the sum of x to the power of n minus 1 times 1 minus 1 plus x to the power of n minus 1 minus 1 times x minus 1 plus x to the power of n minus 2 minus 1 times x squared minus 1, and so on. All right, over x minus 1 squared. So we'll just express this in form of a sigma. So 1 over 2n, x approaches 1 over x minus 1 squared. So this would be just the sum k equals 0 to n minus 1 of x to the power of k minus 1 times x to the power of n minus k minus 1. Okay, so why is this good? Because both these terms are divisible by x minus 1. All right. So every term, so instead of having limit of a sum, we have sum of limits. We will have sum of limits. So this is x to the power of k minus 1 over x minus 1 times this guy. So yes, instead of having limit of a sum, we can have sum of limits now because every limit exists. So we can switch limit and the sigma notation. Okay. X minus 1. So yes, every one of these exists. A limit of x to the power of k minus 1 over x minus 1 is just k. So we get 1 over 2n and this sum, which is equal to k times n minus k. So we have to just evaluate this. And this we can evaluate by the standard formulas. So first part of it is just n times the sum of k terms minus sum of squares from k equals 0 to n minus 1, and here from k equals 0 to n minus 1. So both of these are well known, and these are just equal to n times n minus 1 times n over 2, and minus 1 over 6 n times n plus 1 times n minus 1 times n times 2n minus 1. So minus, yeah, so now we just have to, well, first we can factor out n from here and here, and this will cancel with this. So we just have 1 over 6 n minus 1 times 2n minus 1. Oh yeah, and we can factor out n minus 1 as well. So this would be n minus 1 over 2. And we can factor 1 over 2 as well. So this would be n minus 1 over 4, n minus 1 over 6 to n minus 1, okay? Which is just n minus 1 over 4 times 2/3 of n plus 1 over 6. No, this is 1/3. Yeah, 1/3. And this is also 1/3. So this is our polynomial, basically. So we just have to plug in n equals 0, which would give us the answer minus 1 over 12. Yes, so, okay, this was problem number 2. This took longer than I expected. So I don't know, Meng, should I continue, or should I, what I could do is just, I could send the 2 other problems in the form of notes. You can just give me the mailing list and I can do that. Should I continue, or should I send them in the form of notes? Either one is fine with me. Meng, hello? Are you there?
Hello.
Yes.
Hi, Sasa.
Yeah, hello. So this took longer than I expected. So what I could do is, instead of going over time, I could send the 2 other problems in the form of notes. I could just type the solution up and then I would send them to everybody.
Okay, hi, Sasa, you can continue, okay? Don't worry
Okay.
about overtime, okay? I will pay you overtime, okay?
Okay, yeah, sure.
Continue, please continue.
Okay, okay. So yeah, okay. Let's discuss the problem about the polynomial. So yes, in the problem we have a polynomial px given in the form of a0 plus a1 times x minus 1 plus a2 times x minus 2 squared plus a3 times x minus 3. So the problem says x minus 3 to the power of 4, but I assume that was a typo. So this should be 3. So a4 is going to be x minus 4 to the power of 4. All right. So also we know we're given the information that the second derivative of p is equal to 2 plus 4x plus 4x squared. So yeah, the third information that we're given is that p prime of minus 3 is equal to minus 24. Okay, minus 24. And we also know that if x1, x2, x3, x4 are the roots, then the sum of third degrees is equal to the sum of fourth powers. Yes. So yeah, so these are 3 conditions we're given. So we'll start with the first one and we'll see what it means. And the reason for that being, so if you take a second derivative of the polynomial, then these 2 coefficients disappear. So we will have some condition on the last 3 coefficients, and it will be basically a system of linear equations on a2, a3, a4. So we could just find the exact values of a2, a3, and a4. So so the second degree of polynomial px is just going to be 2a2 plus plus 6a3 times x minus 3, and then plus 12 a4 times x minus 4 squared. So this one is just, we're differentiating and we're using the formula of the derivative x to the power of n is equal to n x to the power of n minus 1. So this is how this formula was obtained. Okay, so, and we know that this guy is just equal to 2 plus 4x plus 4x squared. All right, so now note that this formula is given, like this is a regular polynomial. So we just have powers of x with corresponding coefficients. So this is not the standard form of polynomial. So we will first express the same polynomial in standard form, and then we will equate it to this polynomial, and we'll have a system of 3 equations. So the free term of our polynomial is equal to minus 18a3 plus minus 192a4 this will be our free term. And so the coefficient of x will be 6a3 minus 96a4. And the coefficient of x squared just is going to be just 12a4. So this is supposed to be equal to 2 plus 4x plus 4x squared. So by looking at the coefficients, we can conclude that 12a4 is equal to 4. So this will be the coefficient of x squared. The coefficient of x, these have to be equal as well. So 6a3 minus 96a4 is equal to 4 as well. So 2a2 minus 18a3 minus 192a4 is equal to 2. So this is just a linear system of linear equations with of 3 linear equations with 3 variables. So it is pretty straightforward how to solve it. I'll just write down the solution. So the solution is a4 is equal to 1/3, a3 is equal to 6, and a2 is equal to 23. So these will be the values of the coefficients. Yeah, so it's good. So we just have, now we just have 2 unknown coefficients, a1 and a0. Okay, let's look at the second condition that we had. P prime of x will be equal to a1 plus 2a2 x minus 2 plus 3a a3 x minus 3 squared plus 4a4 x minus 3 cubed. So we have to evaluate this at a point minus 3. All right. So at the point minus 3, this will be equal to a1 plus p of minus 3 to a2 of minus 5. Yeah, and let's plug in the values that we just obtained. So this will be a1. A1 is still unknown. So plus 2a2, which is 46 times minus 5, plus 18 times minus 6 squared, plus 4 times 1/3 times minus 7 cubed. Yes, so, and this is supposed to be equal to minus 24. So we just have to calculate the value of a1. So a1 will be equal to minus 24. Minus 24 plus 46 times 5. Yeah, right, minus 24 plus 46 times 5 plus 18 times 6 squared. No, minus 18 times 6 squared. Okay, and plus 4 times 1/3 times 7 cubed. So yeah, we just have to calculate this value. And yeah, I'm gonna just write down the answer for this. So it turns out to be actually pretty neat. So it's 46/3. Oops. So yeah, this is our value for A1. So now just A0 is unknown, and we haven't used our we haven't used our third condition. Yeah, so now we just have to figure out how to use this one. So if you're familiar with symmetric polynomials, then you know that any symmetric polynomial can be expressed as a can be expressed in terms of elementary symmetric polynomials. So for 4 variables, these elementary symmetric polynomials are so sigma 1 is equal to x1 plus x2 plus x3 plus x4. So sigma 2 is equal to the product of so sum of all products of 2 variables. So sigma 3 is equal to so the sum of all possible products of 3 variables, and sigma 4 is sum of all possible products of 4 variables, which is just the product of x1, x2, x3, x4. So the sum of 3rd degrees is a symmetric polynomial, and the sum of 4th degrees is a symmetric polynomial. So these guys can be both expressed in terms of elementary symmetric polynomials. So we're going to do that, and by equating these expressions, we will find our A0, right? Okay. Also, what's nice about these symmetric polynomials, why do we care, is that if we have a polynomial of the form x minus x1, so if we write it as a product of differences between x minus x1, x minus x2, x minus x3, x minus x4, so x1, x2, x3, x4 are its roots, then, and this is called the Vietnamese theorem. So the coefficients of these polynomials will be these symmetric polynomials, either with a plus or a minus sign. So, and then plus sigma 2 x squared minus sigma 3x plus sigma 4. So this is just it's called Vietnamese theorem. I don't know if you guys are familiar with it. Yeah, but this is you can just open all brackets, and this is the observation. This is a conclusion that we get. All right, so yeah, how is this helpful in our case? This is helpful because we already know all coefficients except for the first one, for A0. So we know sigma 1, sigma 2, sigma 3. We know all sigmas except for sigma 4. So yeah, let's just calculate the values of sigma 1, sigma 2, sigma 3. Okay. So yeah, our polynomial looks like A0, A1, x minus 1 plus A2, x minus 2 squared plus A3, x minus 3 cubed plus A4 times x minus 4 to the power of 4. So the free term will have a form of A0 minus A1 plus 4A2 minus 27 A3 and 16 squared, 256 plus 256, A4. This is our free term. So then the coefficient of x will be equal to A1 plus 4A2 minus plus 9A3. No, 27 A3. And plus, so 4 to the power 3, and we have to multiply this by 4. So this is again 256 A4. Okay. Yeah, all right. Then the coefficient of x2. This is going to be equal to A2 plus minus 9A3 and plus so 6 times 4 squared, 96, I think. Yeah, 96. A4. So the coefficient of x cubed is going to be equal to A3 times plus coefficient of F4 is going to be equal to 16. 16A4 plus x4, just A4. All right, so then sigma 1 is going to be equal to A3 plus 16A4 divided by A4. So we already have the values for A1, A2, A3, and A4. So yeah, let's just rewrite them here. So A4 we know is equal to 1/3. A3 is equal to 6. So 6, 23, and 46 over 3. So 6, 23, and A3 is 46 over 3. So this guy is going to be equal to 6 plus 16 over 3 over 1/3. So 18 plus 16 is going to be 34. All right. Sigma 2. Sigma 2 is equal to this guy divided by A4. So it is just A2 minus 9 A3 divided by A4 plus 96, which is equal to 23 minus 9 times 6, which is 54. 23 minus 54, 31. Minus 31. And divided by 1/3 plus 96. So this is going to be just 3. Yep. Okay. sigma 3 is going to be equal to this guy, 427 to 56. So A1 plus 4A2 plus 27 A3 divided by A4 plus 256, which is just, okay, so A1 is equal to A1 here. So A1 is equal to, it's going to be equal to 46 plus A2 we have is 23. So it's 12 times 23 plus 27 times A3. So 27 times 6 plus 256. All right. So this is a coefficient of x. Yeah. Wait. Is this correct? Minus. Yeah. Okay. Yes. So this is gonna be equal to 23 times 12. So 40. So this is sigma 3. All right, and sigma 4 is unknown yet. Okay, so now we want to express the sum of cubes in terms of sigma 1, sigma 2, and sigma 3. So it is equal to sum of squares, where e goes from 0 to I goes from 0 to 4. Sum of squares times the sum of x's. So note that we're overcounting some terms, so we have to subtract them. We're overcounting terms of the form xi squared xj. So for I not equal to j, we're overcounting these. Okay, so now we will try to express this guy in terms of symmetric polynomials. Yeah, so first of all, sum of squares is just sigma 1 squared minus 2 sigma 2, because this is just the sum of x's squared minus 2 times all pairwise products of them, sigma 1. So this guy, now it is equal to sum of xi, I goes from 0 to 4, from 1 to 4. Times xi, xj, I from 1 to 4. Yeah, so this is just sigma 1 and this is just sigma 2. So we're overcounting certain sums. So first of all, every term of this form is generated twice. So we have to subtract 1/2 of these. And so we have to add the terms that we overcounted. So we overcounted terms of the form xi, xj, xk for I j less than k. So which is basically sigma, this is sigma 3. So we get an inequality. So the sum of cubes is equal to sigma 1 squared minus 2 sigma 2 times sigma 1 minus 1/2 sigma 1 sigma 2 plus 1/2 sigma 3. All right. Yes, so this is sigma 1 cubed minus 5/2 sigma 1 sigma 2 plus 1/2 sigma 3. Okay, so we know the values of all of these, so we can just calculate this sum of cubes. Okay, so sigma 1 is equal to 34. So this is equal to 34 cubed minus 5/2 times 34 times sigma 2 is equal to 3, and then plus 1/2 of 740. Right, so yeah, by computing this sum, we get 1 second, the value of okay, 39,419. So this is sum of cubes of the roots. Okay, now we will do the same thing, but for the fourth powers of the roots, and we will be done because we will get an equation on sigma 4. So we will calculate the sigma 4 from this, and then we will find a0 from the value of sigma 4. And then we will be done. So this guy is equal to, so again, we follow the same strategy. We just, we want to reduce, so how do we do it? We want to reduce the maximum value of the polynomials that we're dealing with. So at first, this maximum power is 4. So now we want to decompose it into the product of two polynomials with powers that are less. But now we're overcounting certain terms of certain certain form, and this form is this. So we'll just leave this as it is. In fact, we can just plug in the value for it. And this guy will be sigma 1. Okay. So this is minus and minus the sum. So this sum, we decompose into sum of guys like these. So again, note that the maximum power is again less because the maximum power of the expression here is 2, and here it is 1 for every the maximum power and the monom that we're dealing with. So yeah, so again, we're overcounting certain terms. So first of all, every term of this form appears exactly twice in this product, so we have to take this sum with coefficient -2. And this is equal to this minus so oh yeah, and we overcounted the terms of the form of this form basically. So xi squared xj xk for I jk. So yeah, the sum of squares we already know that is equal to sigma 1 squared minus 2 sigma 2, and this is just the sigma 2. All right, so now this sum we can try decompose it into these two sums. So it's the sum of all roots and sum of all possible products of 3. So, but we are overcounting every term. So every term appears of this form appears 3 times. So this will have a coefficient 1/6. So now, and then we overcounted the product of all roots appearing it appears 4 times because it is x1, x2, x3, x4, x2, x1, x3, x4, and so on. So 4 times this sum appears, so we have to subtract it and with a same coefficient. Okay, so we just decomposed. So now all these are expressible in terms of sigma. So we just found what we were looking for basically. So 39,419 sigma 1 minus 1/2 sigma 1 squared minus 2 sigma 2 sigma 2 plus 1/6 sigma 1 sigma 3 minus 2/3 sigma 4. So this is our expression. We know it is equal to 3,904.19. So yeah, we just plug in the values for sigmas, and then we know all of them except for sigma 4. So we will now we have to calculate sigma 4 basically. So 2/3 sigma 4 is equal to 39,419 sigma 1 minus 1/2 sigma 1 cubed plus sigma 2 squared plus 1/6 sigma 1 sigma 3 and minus 39,419. All right. So yeah, we just have to plug in the values again. So what was sigma 1 equal to? Okay, sigma 1 is equal to 34, and sigma 2 is equal to 3, and sigma 3 is equal to 740. So this will be, yeah, we just plug in the values and then we calculate the result. So yeah, let me just quickly check the value. So plus 1/6. All right, so this guy is equal to this value. Okay, so yeah, and to find sigma 4, we have to multiply it by 3 and divide it by 2. So 3856,132 divided by 2 is equal to this crazy value. Right. So now the final step. So we know how sigma 4 is expressed in terms of coefficients. So we already know all these, and we have to just find A0. So yes, so A0 will be equal to sigma 4. Let me just double check something. Yes, so plus sigma 4 plus A1 minus 4A2 plus 27 A3 minus 256 A4. All right. Okay, so sigma 4 is this crazy value plus A1 was equal to 46/3. So minus 4 times A2. So A2 was 23. Plus 27 A3, which is times 6 minus 256 divided by 3. Okay, 27 times 6 minus 256 divided by 3. Yeah, okay. Yes, so yeah, we got the result. So I don't know if there is an easier solution, but I doubt it because the numbers are not really nice. So what we could do is we could try expressing px in the form of x minus a4, x minus x1, x minus x2, x minus x3, x minus x4. And then we could express so yeah, we know a4 already, so we could just use x1, x2, x3, x4 in all of these and this as well, and we would come up with some kind of a system of equations on x1, x2, x3, x4. But I'm not sure that it will be much easier to do than what we just did, because so finding x1, x2, x3, x4 explicitly does not seem like a good option for the reason that well, we know that x4, which is the product of them, is over is almost 2 million. So x1, x2, x3, x4 do not have very nice values. So this kind of looks like a we just bashed it, but I don't see a better option. Yes, so this is for this problem. All right. Okay, so about now the last problem is about Amy traveling on the XY plane following some equation. So we move along the XY plane following an equation. So equation is expressed by x e to the power y equals y e to the power x. Yeah, so e to the power x over x, this is an alternative way of expressing the same equation, just with separate variables. Okay, so if we actually graph this, then this would have this would be like in two pieces. So first piece is so first of all, x equals y is the equation of is a solution of this equation. Yeah, but so the problem asks us for the velocity when the Amy is approaching 1 minus 1. So if we were moving along x equals y, we would never approach 1 minus 1. So we assume that we did not move along this part of the graph. So we assume we move along this part of the graph, where x is not equal to 1 unless x equals y equals 1. Okay, so and basically we're asked to find the magnitude of velocity, which is the derivative of this function. So if we set that x is equal to fx, then the magnitude of velocity in point x, it would just be equal to df dx at point x0. Okay, so we're just asked to find this. So, and we know also that so Amy approaches this point. Oops. 1 minus 1. So it means that if Amy now is located at point x0, y0, then the tangent to the curve at this point passes through 1 minus 1. Okay, so let's see what that means. Yeah, so first of all, we would like to take a derivative. We would like to find the derivative of y. So this cannot be done explicitly because this equation, you cannot express y as f of x for f being like composition of addition, subtraction, division, multiplication, and power. So it is not like a nice function. So we cannot explicitly write y equals some function of x. So that is why we have to differentiate implicitly. And so we just differentiate both parts of the equation by x. So we get d of x e to the power y over dx equals to d y e to the power of x over dx. So on the left hand side, we get e to the power of y plus dy over dx times x e to the power of y. equals dy dx e to the power of x plus xy e to the power of x. Yeah, okay. And this one is also xy, right? Yes. Okay, so now we have to, yeah, from this we can express dy over dx as a function of x and y. So ideally, we want to express the derivative as a function of x, but this is at least something. So we would have some kind of condition on y and x. So this is what implicit differentiation usually results in. So you just have some kind of expression for dy over dx in terms of x and y. Okay, so this is equal to, yeah, so we has the following form. So, and the right hand side looks like this. So dy over dx. Wait, we don't have a y here. We have, yeah, it's just x e to the power of x. And this is, yeah, like that. Yeah, okay. So this guy is equal to y e to the power of x minus e to the power of y divided by x e to the power of y minus e to the power of x. So we just got some kind of an expression in terms of x and y for dx over dy. Okay, so we know that y e to the power of x is equal to x e to the power of y. So this is just x e to the power of y minus e to the power of y divided by y e to the power of x minus e to the power of x. So the thing is, we can factor out e to the power of y in the numerator and e to the power of x in the denominator, and we get something of this form. All right, so also from this, we can conclude that e to the power of y over e to the power of x is equal to y over x, which means that y over x times x minus 1 over y minus 1 is our result, basically. So this will be the slope of our tangent at any point. So we need this slope, we need our tangent to pass through this point. In this case, the slope would be y plus 1 over x minus 1, because the line passes through x, y, and also 1 minus 1. Okay. Yeah, all right. So we need this to be equal to y over x times x minus 1 and y minus 1. So this is for x and y lying on a curve. So we also know that e to the power of x over x is equal to e to the power of y over y. Okay. So yeah, so we need to, our goal is to find this slope of the line M for xy satisfying these requirements. All right. Okay, so the equation we get in terms of x and y is this following. So x times y squared minus 1 is equal to y times x minus 1 squared. So x, yeah, so x over y is equal to x minus 1 squared divided by y squared minus 1. Yeah, and also we know that this is equal to e to the power of x over e to the power of y. All right. So is that clear why finding a velocity will give us the desired answer? Because if we find a derivative dy over dx, then, and we know that basically the velocity, we know that the velocity component over the x-axis is 3, then the total velocity will be so dy will be 3 times dy over dx. And so the total velocity will be dx. This is actually delta x, not dx. This would be a proper notation. Yeah, so the velocity will be the velocity over x plus velocity over y squared. So this would be 3 over this squared. All right. Yeah, so it is sufficient to find dy over dx to obtain the velocity that we're looking for. Sorry, Meng. I didn't notice it was 5 to 5. Is it okay if I type the rest of the solution and then send it to kids, because I kind of have to go. I apologize for that, but I will not charge you for the extra time I work on the typing.
Sasa, don't worry. I will pay you 2 hours. Okay, don't worry. You did a wonderful job. Thank you so much. I will pay you 2 hours for sure. Okay, Sasa.
Yes. Okay. But
okay. So yeah, okay, just send. Yeah. So how about this? Can you save the note for me? Save the note. The screenshot. The note.
Yeah. I can write it down in the evening.
No. Hi, Sasa. You don't need to write down. You only write down the last one. So the first three is okay. Okay. The first
yeah. Yeah. Sure.
Kevin. Hi, Kevin. Kevin.
Yeah.
Hi. Can you tell Sasa how to save the transcripts, the note?
Do you mean the whiteboard or the
whiteboard? Yes.
Yeah, I know how to share OneNote. Yeah.
Just set the whiteboard. Okay. Only type the last question for me. Okay.
Okay. Yeah. Sure. That works.
Sasa, thank you so much. I will pay you for 2 hours. Okay.
Okay. Yes. Yeah.
you.
Sorry, guys. I have to cut it here. Yeah. But,
Okay, Sasa.
I will
okay.
send you. I'll send you link to OneNote.
Okay. Okay. Thank you so much, Sasa. You did a wonderful job. Thank you.
Yeah. Thank you.
Okay, bye bye.
All right. Yeah. Thank you guys. Okay, I have to go. I'll send you guys all the notes and the rest of the